Everyone, welcome to your geometry play posit. We'll be covering scale factors under Unit 6, and this is our play posit for Monday of this week. And because of our CIP benchmarks in live class on Wednesday, you will have a second play posit this week, but it's going to be very short. I'm hoping both of these will be very short, so it's kind of like having two just kind of split in half. I'm sorry, one split in half. So before we get started, I just wanted to again remind you guys about the STAR reading test and the STAR math test. Those have been on your plans since December 6th, so that testing window has been open for you guys to take those however your schedule allows, but please make sure you have them done by the 21st before you go on winter break. Thank you so much. Some other reminders, don't forget to complete your practice exam in USA Test Prep. Remember, I'm going to be giving you guys a grade for completion on that. It's really a good time for everyone, even if you're exempt from the exam, to be able to see that material all at once in a cumulative fashion. I know I've shared that before, but I want to share it again because sometimes we can get sort of laser focused, right? You learn one skill and you do a quiz on it. You learn a few skills and you do a test on it. Well, this exam is encompassing everything we've done for this first semester. If you are taking the exam, don't forget that is due by actually 12/16. Let me grab, there we go. Thursday, 12/16 at 11:59. And then our semester 1 end date for everything else, which remember, you don't have anything new on the plan all week. Nothing new. Our last new item was last Friday. That was the Unit 6 test. So you guys should be using this week to get that practice exam done. Take the exam if you are doing that STAR test, right? Math and reading. And then using the rest of the time to review and retake anything or complete any missing assignments. Don't forget, we still have office hours. Those are on Wednesdays, and reach out with any questions, of course. So today we're going to be using ratios to describe scale factors. And if you're not sure what these words mean, we are going to be going over those today as well. So we're going to go through each of these steps to recall a few things about shapes and ratios and proportions, and then we're going to practice some expansions and contractions. Sorry. Professor Akbar has a message. It's a trapezoid. So, quick poll. Recall polygons that have the same size and the same shape. What do we call polygons that are the same size and the same shape? Are they triangles? Are they congruent? Or are they similar? So same size and shape are congruent. Like they're exactly congruent. So here are two, just one example. Hold on. I can do better. Watch. What? My pen just literally drew the wrong way. You guys. All right, so all the angles are equal and all the sides are equal. In this case, these will be equilateral triangles. What is wrong with this pen? I need someone here to help me. See, I promise I drew that line straight. Here, let's do this. I have other tools at my disposal, although I don't think that at this point you guys need me to draw these shapes because you understand what's happening. But when you have congruent shapes, all the sides are going to be the same and all the angles are going to be the same. And we're going to recall today what similar shapes are. All right, check it out. I just made some congruent rectangles. If my pen would work. All right. Congruent rectangle. Same size, same shape. Here's an example of congruent polygons. Remember, it can be any polygon, equal sides and equal angles. Do you guys remember CPCTC? Remember, that stands for corresponding parts of congruent triangles are congruent. Well, we can use this theorem or thought process for any polygon. It doesn't have to be triangle. So you can match up all these parts, right? HG is congruent to UV. Angle I is congruent to angle Z. We're just matching, angle L is congruent to angle Z. We're just matching up those markings. And we say congruent because they're not the exact same shape, right? This is shape number 1 and this is shape number 2. One last thing here is when you know that the shapes are similar, remember we can write that similarity statement. That's the really powerful statement that helps us match up all the sides and match up all the angles. And we could write that by going in the same order on both shapes. So we could go L, see 1, 2, let's see. There's a lot of markings on here. So I think it would go L, K, J, I, H, G is similar to, let's find the 1V2. 1V, here it is. Z, Y, X, W, V, U. And this statement would help us match up all of those corresponding angles and sides. So we're going to use scale factors in a really cool way, I think. You can use them. And a lot of us nowadays don't use paper maps. Maybe you use MapQuest and you're familiar with that. I don't even use MapQuest anymore. Now I just use GPS on my cell phone. But it's the same idea. So here's a map, and they always give you a scale. Hence the term scale factor that we're talking about today. And if you guys did, if you are in Geometry Honors, we did a project where we did scale factors with a candy bar. So this is kind of relating to that. Actually, it is relating to that. You can see it's kind of small, but it says 0. I think it's 0 to 30 miles is an inch. So if you were to take an inch and place it on the map, you would be able to see, oh, these 2 points are actually about 30 miles apart. Now, the paper itself is not 30 miles, right? Because that would be huge. Here's another example. My dad is a home builder, a custom home builder, and he edits home plans all the time. I don't know if you guys have ever seen blueprints for a house. They used to lay around my house all the time growing up, and they are still all around his house. They're on huge pieces of paper, probably about the size of like half of the, like a average size kitchen table, maybe like for a 4-person table. So they're pretty big, but they're still not as big as a house, right? So they do the drawing to scale. You might hear the phrase to scale. So something in real life could be 120 inches, but on paper it's only 10 inches, or if you're going to do a 3-dimensional model. So scale factors are really helpful in real life, especially with architecture and maps, models. So before we get to those, I just want to review what is a proportion. So a proportion is the comparison of 2 ratios. So here's an example of a ratio, 1/2. Or some people write it 1:2. Or you can see a ratio as 1 to 2. Or miles per gallon, right? Like 9 miles per gallon is another way you can see a ratio. It's just a fraction, really. And a proportion, so let me write that here. This is a ratio. A proportion is a comparison of 2 ratios. So you might have like 1/2 equals 2/4. That's true. Or 3/7 equals, I don't know, 12/28. And I multiply both of these by 4 to get that, by this scale factor of 4. So we're going to use the ideas of ratios and proportions a lot in this lesson. So just to review about similar figures, we talked about it previously with the congruent figures, but remember, similar figures have the same size, but different, the same shape, but different size. Just like the house we saw, the model was smaller than the real house. It was the same exact shape, but it was a different size. So you might have a small triangle and a big triangle. And we know that they're similar if the angles are equal, or congruent, and the sides are proportional. This is a review from a previous lesson. Proportional. So if the sides are proportional, remember we set up those proportions, and if they are all equal, then they are in fact similar. And when they're similar, we can use all the different proportions to find missing angles and missing sides. Here's my favorite example of dilation. Have you guys ever gone to the eye doctor and had your eyes dilated before? Likely you probably have. You can see here this person's right eye, because they're looking at us, was dilated, not their left eye. This is so freaky. Usually when you go to the eye doctor, you get them both done at the same time. But this is a great example of showing how the pupil is the same shape, right? They're both circles, but this one is expanded, obviously larger. All right, so let's talk a little bit about some terms for this lesson. We're going to talk about dilation. That's just a process of changing the size without changing the shape. And I'm going to grab my text tool. Why not? Save you guys save me the time of my pen not being great. It works much better in Neuro than it does here for some reason. So a dilation is the process, add this to your notes, of changing the size without changing the shape. And you can dilate something to be larger, or you can dilate something to be smaller. The center of dilation, so we're going to see, and you probably have seen this in your OMHS, we're going to see two centers of dilation. Most of the time, the center of dilation will be the origin. But sometimes we might dilate around another point in a coordinate plane. And the center of dilation, whether it's the origin or another point, it's just sort of like the hub of where the dilation is occurring. And the dilation is occurring at the same ratio around that center. And you'll see some examples here in a minute. The scale factor is a really important piece of all of this, and that is the measure of the dilation. It's basically a number we assign to the dilation that's occurring. So we can say like, well, oh, how much larger is that circle? Right? Or how much smaller did it change? Oh, by a scale factor of 2. Right? And the word factor is going to be really helpful because we think of factor, I don't know about you guys, when I think of factoring, I think of multiplication, because when you factor, you're trying to get two factors, like factors of 9, 3 times 3. So the scale factor is the number also that's being multiplied by each coordinate. All right, so we can either, remember I talked about how we can either expand or we can contract. And so when you're doing that, you're changing the you're changing the size of the image. And it's a good idea to label it, right? You're going to have your original shape. We call the original shape, let me grab my pen. It thinks I'm still trying to do shapes. The original, we call that the pre-image. And we usually label it with like ABC if we're talking about a triangle. The new shape, after either the expansion or contraction occurring, is called the image. And we label that with primes, A prime, B prime, C prime. And again, I'll show you an example in a moment, but it's just a good idea to have different labeling so you can keep the different shapes separate. You know which one was the original and which one is the new one. So the original is the pre-image, and that kind of makes sense, right? You think pre, before. So it's the original before anything has happened to it. So an expansion is when the scale factor is not a fraction. So it can still be negative, it's just not a fraction. So some examples, it could be 5. It could be -1, but it's not a fraction. A contraction is when it is a fraction. So that's much easier to write, like, between 0 and 1. So some example, obviously, 1/2. So sorry, it's a fraction between 0 and 1. Because, you can have fractions that are outside 0 and 1, like 10/2. That's 5. Or what about even like 4/3? That's 1 1/3. So maybe we shouldn't say the scale factor is not a fraction. The scale factor is greater than 1, greater than or equal to 1. And also, the scale factor is less than or equal to 1. So basically, all those numbers between 0 and 1 are a contraction. Think small, tiny, a fraction. Contraction, fraction. Never thought of that. Okay, so let's practice. Are we seeing an expansion or contraction? So here we're just talking about line segments. I don't want these dotted lines to confuse you. We're not talking about triangles. So here's the line segment AB. In these examples, P is the center of dilation. So is the dilation an expansion or contraction? Remember, we can think of contraction, fraction. And AB is the original, that's the pre-image. A prime, B prime is the image. So we are taking this length AB, and you can see it got longer. And that makes sense because the number is not a fraction. So this is an expansion. Here's another example. Look, it's not a fraction, it's an expansion. That's easy. You can just look right at the number or look at the image and the pre-image. You can see that the pre-image got longer, it got bigger. Here, remember, AB is the original. It's the pre-image, and A prime, B prime. Sometimes they use 2 primes. It's just another way to show a difference in the pre-image, the original. It's smaller, and that makes sense that it's smaller because it's a fraction. So this is a contraction. This one, it looks a little different, right? You can see that our pre-image, the original, is down here, and it actually reflected or flipped over the center of dilation. Rotated a bit too. You can see B is here and it's here. So this is what causes it to be negative. So it kind of looks like it's just shifting and expanding. When the number is positive, when it's negative, it's rotating and flipping. And you can see that it still got longer, so the number is larger. If it had gotten smaller, like let's say it was here, B prime, A prime, then it might be something like -1/2. So it'd still be negative, but it's a fraction. Let's practice. Which scale factor would produce a contraction under a dilation of the original image? So we can call this A, B, C, or D. Remember, contraction, fraction, which one is going to give us that contraction? Is D. That's the only one that's between 0 and 1. While these are decimals that we could turn into fractions, they're larger than 1. So contraction, fraction, between 0 and 1. How about an expansion? A, B, C, or D. So we're looking at for something that's bigger than 1 or less than 1 if it's negative, but not a fraction between 0 and 1. And it looks like the only one of those is C. So it's a fraction, but don't let it trip you up because if you look, it's actually 1.5. And if you need to put this in your calculator, you can, and you'll see it'll give you 1.5. So it is bigger. It's not between 0 and 1, right? So that's going to give us an expansion. So now we're going to do some calculations. We're going to be able to calculate that scale factor. How much is this shape changing? And this might be the most useful part. It tells us that the green shape is a dilation of the black shape. So the black shape, let's call this A, B, C, D, is the original because the green one is a dilation of it. So I wish it were labeled, but we should label it for ourselves. So just by looking at it, you can see that the black shape got larger, right, to become the green shape. What is the scale factor? So how much larger is it? How much did it change? And remember, factor, we're looking for a number that we multiply by to get to it. So let's find the coordinate points of these. This is -1, 1, 2, 1, 2, 2, and -1, -2. All right, now let's look at the image. How did it change? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. -5, 5. Let's look at B. 10, 5. So if we compare the x values, we went from -1 to -5. The y value, -1 to 5. You can compare these, the x value, 2 to 10, 1 to 5. Are you guys seeing what we multiplied each number by to get to the new shape? We multiplied by 5, right? -1 times 5 is -5. 1 times 5 is 5. 2 times 5 is 10. And 1 times 5 is 5. We could do the same thing for these. I bet we get 5. Let's see, -5, -10. Yep, look. -1 times 5 is -5. -2 times 5 is -10. So the scale factor is 5. We multiplied each of them by a +5. Let's try another one. Oops. The orange shape is the dilation of the black shape. So the black shape is the original. It says the orange shape is a dilation of it. So A, B, C, D. You can see the orange shape got smaller. There we go. So let's look at some of our coordinates. -2, 10. We really should just have to compare one of the coordinates, right? They should all match. -1, 1, 2, 3, 4, 5. -1, 5. So how did we change from A to A prime? Now, sometimes I know I said scale factor, you think multiplication, and that's true, but if you are kind of going in reverse, if you're going to a smaller shape, you might think of division. But remember, we're going smaller, so we are going to have a fraction. So it's kind of up to you how you want to think about it. We're going to have a fraction, so we're going to be multiplying the original number by something to get us to the A prime. So 2 times what gives you -1? And 10 times what gives you 5? You can kind of write that out if you want. 2 times what will give us -1, and 10 times what will give us 5. We're trying to figure out how did we get from here to here? How did that value change? And we multiplied it by 1/2. Or, like I said, you basically divided each of these by 2. But because, remember, it's shrinking, our scale factor is going to be between 0 and 1. So to get from A to A prime, we halved it. Same thing from b to b prime. This is 10 comma 6, and should be 5 comma 3 since we're having it, right? Yep, half of 10 is 5, half of 3 is 6. So yep, our scale factor is 1/2. One more, the orange shape is the dilation, so it's getting bigger, so we know our dilation will not be a fraction between 0 and 1. Let's see how a changed from a prime. This is 0 comma 2 and 0 comma 8. Looks like we multiplied both of these by 4. 0 times 4 is 0, 2 times 4 is 8. Let's try another one just to be sure. So this is 1 comma 0, and this is 1, 2, 3, 4 comma 0. Yep, look, 1 times 4 is 4, 0 times 4 is 0. We're multiplying everything by a factor of 4. So now let's talk about when the shape is not being dilated around the origin of center. So here's an example. It says the smaller triangle is a pre-image. So the smaller triangle is the original. Remember, pre-image is original. We can label it A, B, C. Of the bigger triangle. The bigger triangle is the changed one, right? The prime, the image. And we can label that, well, this would also be C prime, B prime, and A prime. C is in the same position. The center of dilation is 1, -1, right here. So, you know, a lot of these other things we've seen, like this one, they've been sort of expanding around themselves, right? See, expanding around itself, kind of like either zooming in or zooming out. This one, the shape is in like a totally different place. And it wants to know the scale factor used to create the dilation. So remember, we went from small to big. So we know it's going to not be a fraction between 0 and 1, right? But look, it's also flipped. So we know it's going to be negative as well. So this is pretty cool. It's kind of like a puzzle. The way we do this is we look at each coordinate point from that center of dilation. Here's the center of dilation again, 1, -1. And we say, well, how did we get to B? Well, B is 2 units long, right? Well, how many units long is B in the image, in the new shape? 1, 2, 3, 4, 5. Wait, should be 8, right? Yes, 8 units long. Okay, so from the center of dilation to get to B, we went 2 in the original and 8 in the new one. Well, let's look at the other ones. 2 and 8. So it looks like for this one, it happens to be the same. We're going to look at somewhere it's not. But it went by a factor of 4. And remember, it's negative, so it is -4. My cat just walked in. You guys, I had to get my cat out of my office. All right, let's look at another one. All right, the smaller triangle is a pre-image. Oh, these are both all the same. That's so interesting. Okay. Of the bigger triangle. So A, B, C, B, A prime, B prime, C prime. The center is at 2, -1 right here. What is the scale factor used to create the dilation? So we're just going to count. How long is it? It's 3 units. And it happens to be 1, 2, 3, 4, 5, 6 units here. Same here, 3 and 6. It's funny, not all of them happen to be this nice. Like sometimes this might be, I don't know, 9. And so you just have to, when you're going the other way, like if it gives you the scale factor and you're trying to draw the picture, I can show you that in a minute. But let's look at this first. So the pre-image, the smaller triangle is the pre-image. It's the original. So we multiplied by 2, right? And it is negative because it is flipped. So what I was trying to just share with you is that if they gave you the scale factor to begin with, like if I had a shape here and they said the scale factor is 3 around the point 2, -1. So we go 1, 2, -1. So that's our center of dilation. And we somehow have to change this shape by a factor of 3. So this is how you would do that. You would find this coordinate point, let's say it's -2, 0. Say, well, where is it from the center of dilation? Oh, it is 1 up and 1, 2, 3, 4 units long. So I would need to do that times 3. This one is 4 units away, so I would make it 12 units away. That'd be huge. And see, A is going to be more than 4 units, right? A is going to be maybe 6 units, so it would be 18 units away. So you would multiply however far away the original point is from the center of origin by the scale factor. And we can do more of those. But that was it, 30 minutes-ish. I look forward to seeing you guys on Wednesday for our Mastery Connect benchmarks. And you will have your play posit on Wednesday this week. I just wanted to give you enough time to get it done since you don't actually have any new material on your plans, and we don't have class on Wednesday for material, right? We have class for the test. So I wanted to give you that second play posit on Wednesday and be short, and then we'll be done. Semester 2 is over, you guys, after Wednesday, essentially. So please, again, reach out if you need anything. I'm happy to help, and I'll see you guys soon. Bye, everybody.